Everyone. The delay in the start, but technology, you know how it is. The simple things are always the most difficult things, like getting a screen to work. But it's a great pleasure to have here today Dr. Ryong Kim, assistant professor in the Department of Computer Science at the University of Texas at Dallas, where he's directing the Multimodal Interaction Lab. And his talk today is about designing multisensory interfaces, which I think resonates with a lot what we discussed this morning at the MSD group, but also the wider UCLIC. And apologies, there is a smaller amount than expected because of the tube strike. Welcome to London. But we have people online as well, so we will monitor for any questions. But I think I will give the floor to you. Okay, Thanks very much for coming.
All right, so thank you so much for having me, Mariana. It's a great pleasure to be here. I always wanted to visit your lab, and also UCL and London. It's so exciting. I really enjoyed all the discussions that I had in the morning. I have a lot of great mind students and also the faculty members. I really enjoyed all the nice discussion. We actually came up with a lot of ideas, across those conversations. So my name is Ryong Kim, and today my talk is about designing multisensory interfaces. I'm sure that you guys all, design and create those user interfaces. So I just made this title from perception to human-centered intelligence. So these days, my work is mainly more focused on perception-based approach, but then my vision is to apply those perception-based engineering approach going into more, AI stuff. Everybody's doing AI, so why not? I was just exploring this area, so I just named it this way. So, let me see. So a little bit about myself. My name is Ryong Kim. So Ryong is my first name. So it actually has two characters, Ryong. Jin is actually means the vibration in Chinese character. So I chose the right, area for my research. And Ryong is, I'm sure you guys know, dragon, right? So it's a vibrating dragon, actually. Kim is very famous, popular last name in Korea. So like 1/3 of the population actually Kims. I'm an assistant professor in the computer science department. Also, I'm director of Multimodal Interaction Lab. I did my PhD at Purdue University. And my advisor is Hong Tan. She's a well-known haptic expert in this domain, and she's now at Google leading the haptic teams at Google. My focus is more onto the haptics, multisensory haptics, also the thermal-tactile perceptions and integration. That I recently put more efforts into this thermal-tactile perceptions, and also the XR interfaces. So my lab is called the Multimodal Interaction Lab. So we're interested in designing the multisensory XR interfaces. We're looking into how human can interact with virtual environment with multisensory feedback, including vision, audio, touch, and temperature. So our goal is to establish the interdisciplinary research collaboration program. We have the students from computer science, computer engineering, electrical engineering as well. We have some students from cognitive science. So we try to collaborate together to really create something, we feel that's novel. So the basic idea is to create an immersive multisensory interfaces in an environment like an XR environment to increase the natural human user experience. So I'd like to start with how we perceive the reality. So we understand the world through our senses, through our sight, hearing, touch, smell, and taste. And more we see the world, we hear the environment, we touch them, we feel them, we smell them, we taste them. It's all about sensation and perception. We try to gather information through our human sensory system, and we interpret the information to understand the world better through our human perception system. So this actually shows a simple sensing and perception model of our physical world that we start through this sensing. We try to sense the world, and then there's a phase of consciousness to understand the information. And then there's a proper action to take based on that understanding. And then it goes back to reality and doing this sensing, consciousness, and action. It's a complete loop that we continuously sense the world and perceive the information. This is the same sensing perception model for virtual reality. It actually shows the very similar patterns that there's a phase of senses that we try to sense the world. There's a consciousness, phase of consciousness to interpret that information. And then based on that understanding, we take the action. And then if we can intercept what people perceive, what they sense from the external world, and replace it with those output devices like HMD displays or haptic display, auditory display, and we can intercept those user actions with those input devices like tracking devices, we can sort of fool the human perception and generate artificial sensations as if they feel that it's real. We can completely replace their sight, hearing, touch, smell, and taste with those artificial sensations to create the illusion of reality, and we call this virtual reality. So sometimes we go out for hiking, try to see things around us. Sometimes we interact with people. Sometimes we go to coffee shop, Starbucks, drink coffee, but at the same time we feel the warmth of the cup or smell the coffee. Sometimes we touch things around us to understand the world better. And you know that this is called the multisensory interaction. And we can use those multisensory interfaces to create the illusion of reality. We can generate those artificial sensations of their sight, hearing, touch, smell, and so on to completely fool the human perception. We can make the people that it feels real. And our lab is mainly focused on haptic interaction, how we can improve the user experience through those touch interaction or haptic interaction. So I'm sure that many of you already know the term haptics, but let's review what the definition of haptic is. So haptic is actually the word actually coming from the Greek word haptikos, meaning the sense of touch. So haptikos means to grasp or touch. So there are two important terminologies in haptics. One is called the cutaneous or tactile, anything that you feel through your skins, whether it's a texture, vibration, temperature, or a little bit of force, we call that cutaneous or tactile. There's another terminology called the kinesthesia, which is related to the location of body in space, where you feel the location, motion, and force. The ability to sense the motion of joint, we call this kinesthesia. So this picture actually shows very nice description of those two terminologies. So person is holding a cup with one hand, another hand he's holding a jar, and he's trying to pour the water inside the cup, right? So he probably feel those texture of the cup or the temperature of the cup through his skin, right? So this is called the cutaneous or tactile. Whereas he's holding a jar, he feels the motion, he feels the weight of the jar, or the force that he's trying to pour the water inside the cup. This is called the kinesthesia. So haptic information is basically the combination of cutaneous and kinesthesia. Let's look at some of the today's haptic tactile feedback. So many of people actually use those, LRAs, ERM. Some of you work on haptics. You guys probably know about this. It's very, small component. It's like a motor-based piezoelectric actuators that actually can reflect itself by applying high voltage. It's easy to manage. You can just apply. You can find it using your phone or some VR controller with those, actuators can do some vibration, right? It's mainly all rely on vibration. There are some other actuators like pneumatic actuators or EMS and so on, but mainly these are the actuators, and great that it can just give you some buzzing confirmation feedback through the skin. Those are the main major components. And are they enough to really replicate what we perceive in the physical world? Well, those are very limited, expressing in those touch sensations. We have very complicated, touch feedback that we experience in our physical world. If you touch something like a, hard rock, you can actually feel very rough, but also at the same time, quite cold feedback. Sometimes you try to experience some raindrops. I'm sure that many of you, have some kind of experience of raindrop splashing on your palm, right? Sometimes we come closer to the fireplace to feel the warmth. Sometimes we interact with other people holding their hands. Can we present this using vibration? Not really, right? So my journey initially, when I got into haptics domain, I thought that vibration sucks. I really hated vibration. I wanted to do something different, like, vibration is just vibration, even though my middle name is vibration. So I wanted to do beyond vibration. How can we deliver more realistic feedback, haptics touch sensation that is beyond vibration, something else that can we use something else? I like to, give a little bit old project that I did. It's called the Real Walk, but I thought that will be a very interesting topic to discuss. So it's a haptic shoes for VR. So we presented this work at CHI 2018 as a demo, and then we presented as a full paper at the journal and so on. But mainly the idea here is that people walk all the time, right? We walked on the street for 10 minutes to get here. We also walk on the different conditions, ground surface condition. We sometimes walk on the carpet, sometimes you walk on the sidewalk. You actually feel different feedback, right? Sensation from the floor. That is very obvious. Even though you wear shoes, you can definitely tell the difference between how you walk on the carpet versus how you walk on the street, right? So we walk every day. Sometimes we walk on the sand. We walk, go for hiking on the mud. Sometimes we walk on the snowfield. When we walk, we actually feel not only the ground surface feeling, not only the texture of the ground, but also we feel the surface deformation, right? Sometimes you feel no surface, sometimes you feel some surface deformation. So our question is, how can we create more natural walking VR experience in VR? Can we naturally deliver those ground material sensations and surface deformation at the same time? How can we really simulate this kind of different behaviors of the ground surface materials? And we explore some of the options here. And we found very interesting smart material, smart liquid, which is called the MR fluid. This is actually used for the car brake. So it's basically, it's oil that comes with the magnetic particles. You mix it, it becomes a, smart fluid, MR fluid. So it's a type of smart fluid that it can increase its viscosity when subject to a magnetic field. So it's very fascinating, material that we can adapt into the VR experience that could replicate some realistic walking and feeling the ground surfaces. So we made the haptic shoes. We used the sandal type so that everyone can easily put on, and then we put the vibe tracker so that we can track the location of the shoes. And then we attach those link structures. So, the people, they don't just walk straight. Like everyone walk all differently. We had to balance those pressures between two movements of the walking. So we had this link structure, and then we put two MR fluid actuators. So this actuator is custom made. We made this actuator, put the MR fluid inside the actuator, and we changed the viscosity. So we had this MR fluid actuators, and in between we put the spring in between so they can recover once it's pressed. This is the MR fluid actuator. I'm not going to talk about too details about this, but the basic idea here is that there's a chamber that contains the MR fluid, and then we stack the disc to create some sort of path here. And then around this path, we put the magnetic coil. That's a very simple design. And then whenever this actuator is pressed by a human foot, then this liquid, the fluid, actually goes up, travels. And at the same time, we apply the magnetic field to control the viscosity so that we can create sort of like crispy sort of feedback. And if we do well on this rendering, we could quite well replicating those realistic feedback. This is a little bit story, but we made the footstep detection and haptic rendering as well. We used the vibe tracker, and we also used the insole pressure sensor so that we can detect the moment that when the shoe is landed on the ground so that we can give a right haptic feedback. We designed 4 different VR scenes, spring for the representing the grass, summer with the sand, and the fall with the mud, and also the winter for snowfield. Let me show you the video that we presented at CHI. This fluid, right? And this is a magnet and that becomes solid instantly. And then when we remove the magnet, it becomes liquid. So we can, change the viscosity to create those snow feedback, mud feedback, and even the solid ground feedback as well. And this is actually shows the insole pressure sensor that how we can detect when it is landed on the ground. So he's wearing the haptic shoes, and he can walk on the sand or the grass. People actually love this snowfield walking. It's very realistic. Then I would sort of get into more realism. I just joined UTD, University of Texas at Dallas, after spending years in Alibaba and Korean national labs. I wanted to do a little bit more realism. How can we sort of create more realistic feedback? And at that time, I was so fascinated about the mid-ear haptics, ultrasound haptic display, and I wanted to do a little bit more, combining some other modalities together. So the first project I like to talk about is called the FIRE. So we finished this project during the COVID year. So I think it was 2021. We presented this work at VRSD, but then because of the COVID, we couldn't really demonstrate the work. But then, when the COVID is a little bit over, we decided to sort of showcase the work. We also showcased at many places, including the SIGGRAPH Asia 2023, and we actually won the Best Demo Award at the Emerging Tech. So idea here is to really create a very real experience. Our question is, how can we bridge the gap between the physical world and virtual world and create an interface that actually replicates the sense of touch to provide a very compelling experience? Then we were thinking about what is real, right? So when we look into some other touch feedback that we experience, we thought that it's not just one single modality that we feel like a cutaneous feedback, but it's actually combined, not just only one, but actually combine those. And we are interested in how we can naturally combine the thermal feedback with the tactile feedback. How can we integrate those two modalities together to create more compelling user experience? So this is actually the perception-based approach that we combine thermal and tactile feedback in midair. We used, I'm sure that many of you already know, the ultrasound. So we use the ultrasound to provide a localized tactile feedback. And then we use this chamber style to keep the heated air inside the chamber as a global temperature feedback. Then we thought that it could naturally combine those two modalities together to give a compelling sensation. So because it's a combined unified perception, people actually enjoy this kind of warmth with some localized cue. So we made this fire display. We used those chamber to keep the heat inside the temperature and to control those temperatures. We use those heat modules to generate those heat. And then we use the ultrasound. It's a very simple setup, but it's quite compelling. Oh, you don't mind the sound, so I don't know how to volume down. Sorry. Okay, I think this is good. Yeah. So we also measured the user temperatures. We made those some VR scenes interacting with the water, hot spring water, interacting with the fire, the campfire. The attendees really enjoyed this campfire, that they just keep saying that we don't have to go to, the mountain to experience it. It was very interesting to interact with sort of like a steam. And then people kept asking me, what about cold? Because they experienced hot, it was good. What about cold? And we thought that it would be cool to sort of make the cold feedback as well. And, that actually get us to the snow system. So in Texas, we don't see much snow. I'm sure you guys have a lot of snow during the winter. No, not really? Oh, okay, so you should need this system as well. So then I thought that this will be very interesting to sort of make the snow system in Texas. People might enjoy during the summer. So we decided to design this snowfall experience in VR. So we actually presented this work at the IMWT UBCom. So this is a snow system. Everything is very similar. It's just now the display is upside down because the snow is actually coming from the sky, right? So we made the ultrasound display upside down, and we made a huge chamber to keep the cold air. And we designed this Peltier pack. We customized this Peltier pack to create a cold feedback inside the chamber. This was very, very challenging compared to the heat system, fire system. But we actually made it, and we actually got very interesting user experience as well. So we wanted to do a little bit more. So we did some, software side. So we did some snow rendering. So we have visual rendering. We tried to sort of match the real world, how the snowflake as well, and sort of exaggerate it a little bit. So we made an interactive particle system that has around 70% landed on the palm, 30% on the finger, and then the size might be randomly varied with the fall speeds around 0.24 meters per second. And then for the haptic rendering, we used the circular cue with a modulation frequency of 120 hertz. And then we wanted to create the snow melting on the palm. So initially we get the big cue, circular cue, and then the intensity actually decay over time so that they can feel like it's melting. We created this multiple snowflake rendering because there may be, light snow, but sometimes you feel heavy snow as well. So for the light snow, we try to do this point rendering. So just get the 1 point at a time. And then for the heavy snow, because the ultrasound display has a limitation, cannot create more than 10, 11 points. So we just cluster them together so that they can actually feel it. I think you have a very similar paper. I remember that it's about rain or snow, that how many. So we actually got some insight from your paper as well. But we also made the rain system. It's very similar things, but rain is also considered as a little bit cold. So we made an interactive system to have 70% palm and 30% on the fingers, and then we have a fall speed around 0.2 to 0.7. And then we wanted to render this raindrop splashing. So visually, you will see the raindrop and then it will be splashed. So that's how the rain actually rendered in visually. And for the haptic feedback, we increase the size from 0 to 40 so that you can feel like it's getting bigger and larger, but we keep the same intensity as 100%. And we also did the point-based rendering and also the aggregation. So this actually shows some videos. That's the system. The interaction space is very little. They can just do this, but they can actually feel very nice snow melting. That's the rain that actually they can feel it as well. All right. Now then, I was going into some tangible user interfaces. I was sort of interested in going into some tangible user interfaces. I made some couple of the interfaces, made the prop type, which actually can turn your any everyday object into the keyboard surfaces. That we presented this work at Kai last year. Sensory blocks is like a Lego style tangible interface that I'm going to show you right away. Some ultra edit, I really wanted to share this as well, but then I have limited time and wanted to show more, so maybe next time. But it's very interesting authoring tool for ultrasound haptic display that you can use like a blob to create your own haptic profile and design the haptic for 3D object, and then some other projects. So the project that I like to talk about is called the Sensory Blocks. It's a plug and play, plug and fill modular multisensory user interface for immersive cardboard VR. So this work is actually, so each block here represents sensory feedback. So we have a vibration module that you just give a vibration. Some modules have heat. It has a thermal actuator inside. Some of the modules have fans, so you can have a wind feedback. Some of the modules have olfactory, so we can actually also smell. So we designed this for kids. For the cardboard VR users, so cardboard is very cost-effective, design, so that it might be very useful for kids. So they can make their own VR controllers to use it for VR cardboard, so that they can play with it. So this is the modular user interface. These are the modules. Here my student actually made the shooting gun for the VR game. It's a multisensory. It's low cost. We aim for low cost. It's reconfigurable. You can always, detach and connect them together. It's scalable, user friendly. A little bit about the hardware system. It's a cube style with 30 millimeter in height, width, and depth. It has those magnets so that it can easily snap together with those blocks. We use this VCC 3.7, data communication, and the power distribution, and so on. So this actually shows the module type. So we have a fan, the heat, tactile, microcontroller. Also, it's all standalone olfactory system. And we have so these are all the components: central, vibration, thermal, airflow, olfactory, and some dummy as well. And then it has a battery as well. We also made a software, so we need to be able to, sort of customize the haptic profile and so on. So we have those modules scanning. So once the user wear the VR cardboard, they can use the phone camera to detect the shape of the module with some marker design. So those, the blue circle and triangle, those are the markers that you can easily detect using the computer vision. And then we have those interface design to easily detect the shape and then customize on the way. And then we design 3 different VR scenes to check the usability. This actually shows the user workflow. So they can just make their own VR, and then once they're finished, they can scan it, because they don't have a controller VR cardboard, so they need to use the reticle pointer too. But it works very well that they can, use the VR controller to, this is the trumpet. But then, these approaches actually aim for realism. I was trying to really focus on achieving more realistic experience. But then they all rely on those hardware scaling, right? Can we do better than that? Then I got into more exciting area, which is called illusion. This is actually very fascinating area that I actually discovered. We are very excited about this new discovery that we actually named it as thermal masking illusion. I think this is the most highlight of my talk, which is called the thermal masking, and also other work that is related to that thermal masking. So I'd like to share this work with you guys. So thermal masking, we presented this work at CHI 2024, 2 years back. We named this thermal masking illusion when the illusion takes over the real. This is the new illusion that we discovered, sensory illusion that we discovered. We actually won quite a bit of demo awards using this approach. So let me start with this statement. Designing thermal user interfaces is extremely hard. It's because I mentioned about haptic tactile actuators. There are LRA, ERM, piezos. These are very, cost effective. You can just get it those actuators from 100 pieces for like less than $10 from Amazon.com, right? You can just easy to get. Like it's just the motors that you can actually feel it. Whereas thermal actuators, it's so complicated. It needs a heat sink. It's bulky. It needs a lot of power consumption to create the heat and cold and so on. And it's huge. It's not easy to attach to your body if you want to provide a temperature feedback on your body, right? So it requires power, right? During the winter time, you probably need more money to pay your bill, right? For the power. So it needs power. It is complicated. You have more complicated circuits. You need more, size and so on. It's so complicated. Those Peltier setup with coolers and circuits, it's very complicated. That comes with the scalability issue. If you want to scale, if you want to apply heat, you want to give a heat here, but then what about here, here, here? You probably need a lot of Peltier devices to cover, and that actually costs a lot of complexity and also the money and so on, right? So it's expensive. This costs a lot. Thermal actuators are already expensive compared to the tactile actuators. Thermal actuators actually, the cheapest one probably $100 to $1,000. It's very expensive. And what we found is that we actually accidentally found this phenomenon, but when we apply the heat at some place in your body and apply the vibration nearby, you can actually feel the very vivid, clear thermal sensation at the vibration location. When I first presented this work, nobody actually believed me, but it actually works very well. That if you apply heat, vibration, you're supposed to feel heat at the heat location. You're supposed to feel the vibration at the vibration location, right? That's a common sense. But you actually feel the heat at the vibration location. Isn't it amazing? So brain actually get confused where the heat is coming from, so that they believe that heat is actually coming from the vibration, not at the heat location. So we thought that, oh, this is really, really super interesting discovery. We should name this as thermal masking. Why we name thermal masking is because this heat is illusion, right? It's not real sensation. It's actually an illusion that you actually, feel it. But this heat sensation is so strong that you actually forget about your original heat sensation. So this illusory heat can dominate original heat sensation so that you can actually feel the illusion only. Some people feel both, but some people, okay. Oops. What should I do? I think,
Resharing this slide?
yeah, I can reshare. Yeah. But I don't know how to get back to, oops.
On the desktop. No? Oh, if you go there.
Okay, so this is my slide. No, it's not showing.
The other one?
Oops, maybe I can just start from the beginning.
Sorry about that's an illusion.
Wow, okay. So let's see. I got my screen back. Oh, now it's not. Okay, let me start again. Let me see where my slide is. And the show. Okay, so I can reconnect this first.
Interesting. Never happened before.
Okay, maybe. And now I can do this. Yes, and yes, and then I think I need to share the Zoom, which is this one. And then share, I think this one, and share.
Perfect.
Perfect, yes. Okay, so I was talking about it's a fascinating illusion. It is. Trust me, okay? So I believe Mariana tried some of the demos, right? That you feel the tattoo, right? So, yes, so it's a newly discovered thermal illusion that actually shows very clear, vivid, localized thermal sensation, right? And why is it important? Why does it matter? Well, yes. How far? I will talk about this. That's a very good question. I'm going to talk about this. Yeah, just hold a little bit, okay? So why is it important? Well, we can replicate heat with vibration. So if you have one single thermal actuator, for example, on your palm, if you have one tactile actuator, you can have one thermal illusion here. If you have three, you can actually feel three. If you have 9 altogether, you can actually feel the entire palm hot. So with this, we can say power. You don't need that many thermal actuators. You just need one single thermal actuator using multiple vibrations to replicate the heat. That actually solved this complexity problem, right? That we don't need the very complicated circuit. You just need one single thermal actuator with multiple vibration. You can do it. You can scale. Vibration, as I mentioned, you can get 100, 200 pieces less than $10. You can scale. You can just place it anywhere with one single heat source. You can actually give a heat to anywhere you want. And that actually costs a lot of money, right? So power, complexity, scalability, and it actually costs a lot of money, save a lot of money. So if you have, for example, designed the thermal vest with a vibrotactile feedback, if you have 4 thermal actuators and, the vibrotactile actuators, you can actually move your heat sensations to the location where you want to place, right? Even with the single one thermal source, we probably can move the heat traveling through your arm using only one thermal actuator and a couple of the vibrations. So we did the user study to make sure that it works and how it works, in what aspect. So we made very simple thermal masking, environment that where we have a thermal actuator here at the center of the forearm, and then we put the tactile actuator. This is a vibrotactile actuator apart from the thermal actuator. And we did a couple of studies to explore the capabilities and limitations of this approach. So first study, we wanted to see the thermal masking impact illusion on temperature. We wanted to see what temperature actually works better in what sense, right? So we designed the study that we have a one thermal actuator, and then we place the 8 centimeter from the center of the thermal actuator, we place the tactile actuator. And then we had this 4 different temperature conditions. One is cold, so -8 from the skin temperature, -5 as a cool feedback, warm temperature +3, and hot temperature +6. And we explored, we asked them to, we have a bunch of questions that they need to answer, and then we also asked them to draw where they feel the warmth or cold, the temperature at the location, and ask them to draw on the tablet. And it's very interestingly that it actually works across all the temperature levels. So we define some of the terms here. The weak referral, that we define the term weak referral, meaning that they feel the temperature stronger at the original source but still feel the feedback at the remote, the vibrotactile site. We call that weak referral. If they feel more stronger at the vibrotactile site, we call them strong referral. If they only feel the thermal feedback at the vibrotactile location, we named it masking, because it's actually completely, mask dominate the original sensation. So we have cold, warm, and hot here. As you can see, that masking actually very clear with the warm sensation. Also, the hot sensation actually shows very clear. We also discover a lot of strong referral cases that actually feels very strong feedback. Cold actually works as well, but a little bit weaker than the hot and warm. So that was our initial finding. And then the second study that I'm answering your question, we wanted to see how far it can go. Can we go to where, right? So we wanted to see the distance effect. So we chose those 2 temperatures, warm and cold, and then we placed the actuator at 4 centimeter, 8, 16, and up to 24. 24 is up here. And see if that works. Is that because of the closer distance that we actually feel? It actually turns out that masking and referral, the masking actually works very well up to 24 centimeter, that people actually could feel very clear thermal sensation. They can only feel the thermal sensation in these cases at the vibrotactile actuator. So it's very weird. If you test it, if you feel thermal here, it's very weird. It actually shows similar trend, but quite weaker in cold sensation, but it actually works as well. And then the last study, we wanted to see if there's a thermal masking works on the opposite side of the skin. So if we have a thermal sensation, if we have a vibration here, does it work? That's an interesting question, right? So we also tested we placed the thermal actuator at the ventral side, and then placed those vibrotactile actuator at the other side of the skin, here, dorsal side, and then tested. And also worked well. So we're very super happy with those results. Now that back into this diagram that I was talking about, those vibrations sucks. Now vibration becomes powerful when perception is engineered. So I became a big fan of vibration now. So what this actually shows is that we can do this illusion-based XR interfaces, that we can design, something like HMD with the thermal feedback. We can also design this kind of arm sleeve using the thermal masking approach. We can also design this, collar or the necklace style. Vest, of course, we can have a very realistic, thermal sensation using the, vest. And also the haptic shoes. This work is already been very powerful within very short period of time. A lot of papers already follow up. Some of them are ours, those fiery hand, thermal emotion, heat flow, those are all WIS papers that we presented last year and the year back. And then some of the other people's labs work as well. I'd like to share a little bit about the work here. The first one is the fiery hands. We also designed the haptic thermal glove using this thermal masking illusion. So we placed the vibotactile actuators here, and then thermal actuators here, and also the back of the fingers, so that they can do the virtual object manipulation. Here some of the applications. You can have a magical, fireball, or you can wash your hands with the hot water. This actually feels very realistic. Another project is thermal emotion. We actually won Best Demo Award at ISMAR, and also the WIST Best Demo Honorable Mention Award, that we can create this thermal sensation that is moving across your arms, that you can feel the hot motion and cold motion. We can change the speed of the motion. The example here, VR interaction, is that you can grab a fireball. You become an Iron Man, you can grab a fireball. You can actually feel the energy filling up your arm. And this is very recent paper that we presented last year at Heat Flow. We got the best paper honorable mention at WIST. I think Mariana tried this. We actually create a 2D display and create any flow motions using hot and cold. One of the VR applications we designed was the tattoo shop, where you can feel the, fake tattoo with some hot sensations that is moving, that match with the visuals. Yeah, this is the scene that you can actually feel those tattoos. So to wrap up, I think it's almost time. So my vision is to design the interaction to where human interact with human, and also AI agent through those multisensory feedback. And some of the things that doing this is that, we wanted to see why does thermal masking happens? How does it work in the brain? Those are the questions that I really wanted to explore, that might open up some new areas as well, because I found some evidences that some ladies at the conference, she actually lost her sense of touch. She cut herself, so there's a nerve damage. So she couldn't feel for a quite long time since when she was young. Now she tried our thermal glove, where she actually told me that she just told me, so she was so excited that, oh, I could feel the heat here. There was no heat here, heat was here, but she felt heat here. There was only vibration. And I asked her, did you feel vibration? And she said she couldn't feel the vibration. She only felt the heat. So there's something going on in our brain that there might be a sensory map that we really wanted to explore. The next thrust will be designing illusion-based multisensory feedback. We like to leverage this approach to design more richer and compelling user interfaces to give more like a lifelike sensations. Some of the, the work that we are working on is, this HMD style thermal masking device we recently explored that can give some very compelling, immersive haptic experience with the VR scene. And the last one is the embodied and multisensory human-AI interaction. We already started, we presented very recent work about the social touch, how people actually touch each other to carry the meanings. I'm sure that Mariana will we wanted to know a little bit more about this work. And then also how we can apply this into for the AI agent, so that people can interact with the AI agent more realistically. I'd like to finish up with one last video that this is very, very, rough work. My undergrad students actually did it, and they presented this work at IEEE VR as a poster and demo. I really like this work because it actually shows some sort of like a future insights that we can go. So the idea here is that there's an AI agent, and then there's my student, and he's trying to interact with this AI agent with haptic feedback. I'm doing well. Thank you for asking. You want to play Flappy? So basically, he's wearing a haptic suit and he's wearing haptic glove, and whenever they interact with the AI agent, then he can just feel sort of like a vibration. But yeah, so anyway, yeah, that is all I have for today. Thank you so much for having me, and it was a pleasure to be here, and I'll be happy to answer any questions. Thank you.
Truly to the vibrating dragon.
Yeah.
I know we have a bit of time. Effectively, if there are any questions, now it's the time.
So I missed the first part of the talk, but I really agree with your like overall multisensory vision. And for your last part, you envisioned the multisensory feedback for the AI agent. I would like to hear more about your thoughts about it and how can you make a virtual AI agent and make it more like embodied and more real?
Okay, yeah, that's a very good question, and that's something that I am actually, exploring and interesting. Some of the approaches that the first step that I did, so this is like very initial step that I asked my students to make an AI agent and see how the people interact with, and we found very interesting, things that we cannot really do, and the even conversation was a little bit hard. Like we had to wait for the AI to answer the questions and some delays and so on. And but then when we interact with it, and also like some of the haptic feedback was very interesting to experience. So I recently presented work at it's called the social touch. I think social touch with meaning. That what we did was I think I have a video, but I didn't have time to play the video. But what we did was that we wanted to, so we thought that people actually touch each other in a social setting, and that actually carries some meanings. So sometimes you touch the shoulder to give encouragement, or sometimes you touch the arms, and sometimes you touch some other body parts. And what we found very interesting is that some gestures, some of the gestures actually carries the same meaning, or some same gesture carries the different meanings. And it's all about context and also other factors like environment, relationship, so many factors that we discover through this YouTube video. So we collected a large amount of YouTube videos. We processed it using the computer vision, and then we run some AIs to detect the moment when they touch. And then we sort of made some sort of like a taxonomy, and then we did the contextual analysis. We found very, very interesting touch interactions going on that in a social settings. And sometimes people touch their head. What does that mean? Sometimes people touch their face. Sometimes they touch legs. People actually touch legs quite often. No, it's not like rubbing, but like like tapping, or gentle touch in a sitting settings, right? So it's all different, like based on the cultural differences. We collected the videos from Korea and also the US based videos, and compared the those cultural differences, relationship, friends versus strangers, how they do the handshake. what does that mean by touching the dorsal side of the hand or the inner side of hand? It's quite different. So we did those kind of contextual analysis to get started with how we can implement, so that this database can be very useful for designing, the XR AI agent, or it can be also very useful for robotics, how we can design the humanoid robots, so that they can understand and where to touch to, for example, comfort them or to cheer them or so on. So we are very excited to have, studied this kind of direction, and that's sort of hope that I can answer that question.